Every line of code running in the cloud has a physical weight, requiring steel, water, and massive industrial cooling power to keep servers from melting. We have spent 2 decades optimizing software engineering for scale and delivery speed, assuming the physical hardware underneath could handle the load. Now, that code is colliding with hard electrical limits. This chart shows the projected exponential growth of global data center energy consumption over the next 10 years. The energy required simply to keep our applications running is outpacing grid capacity. The proposed industry solution is to turn software engineers into high-value environmental architects. 2 specific technical proficiencies on this list are driving the most aggressive recruitment: carbon-aware computing and smart grid integration. The pitch to developers is straightforward. Master these deep tech systems and you secure premium salaries while directly contributing to planetary restoration. That pitch runs against the ingrained habits of modern development. We are taught to treat compute power as a cheap, infinite resource to be drawn upon whenever our code demands it. Shifting from viewing software as an invisible digital resource to treating it as a physical energy drain requires treating every line of code as a measurable draw on the local power grid. Right now, you could spend your weekend learning to integrate the latest generative AI model or deploying scalable cloud architectures, skills with immediate, obvious market demand. To see if transitioning to sustainable engineering actually pays off, we are going to evaluate these new skills using 3 metrics: the input required to learn them, the financial outcome, and the daily trade-off and friction. Taking on environmental architecture means starting from zero on complex physical systems. It requires hundreds of unpaid hours studying power grid behavior instead of writing standard application code. You have to evaluate that heavy upfront cost objectively. You need to know if this pivot is a profitable career mandate or a dangerous distraction from the core skills that keep you employable. This dynamic matrix scorecard will track our evaluation, starting with carbon-aware computing. Carbon-aware computing is the practice of timing and routing software workloads to run when the local power grid is supplied by clean energy sources. The necessary input involves pulling data from external energy grid APIs to schedule your heavy compute tasks. An API is a set of protocols that allows your application to communicate with third-party servers. The outcome is a measurable reduction in the carbon footprint for heavy batch processing tasks, alongside significantly lowered cloud energy bills for the company. But the trade-off is severe. You are intentionally introducing processing unpredictability and latency directly into your system architecture. Modern consumers expect an application to respond the exact millisecond they quit a button. They do not care if the wind stopped flowing at the data center holding their profile. If you apply carbon-aware scheduling to a real-time user-facing application, the application simply breaks. The system waits for clean power while the user waits on a frozen loading screen. Carbon-aware computing forces a hard architectural compromise. You have to actively choose between optimizing for planetary health and ensuring instant user gratification. Our matrix scorecard updates with a second high-value skill: power-efficient algorithm design. The required input forces you to unlearn the mentality that compute is cheap. It means abandoning bloated frameworks and manually optimizing your code at the micro level to stop wasting CPU cycles. The outcome is a highly efficient, lightweight codebase. The software demands fewer server resources, which physically reduces the hardware infrastructure required to run it. The trade-off is drastically slower developer velocity. Writing code this tightly increases your debugging times and limits how fast you can push updates. This creates intense cultural friction inside rapid iteration teams. Your environment expects you to build, test, and deploy features in fast 2-week sprints. An engineer spending 3 days optimizing a search algorithm to save 10 watts of power will immediately clash with a product manager prioritizing the rapid shipping of that search feature. Adopting power-efficient algorithms breaks the modern tech industry's move fast and break things business model. You are explicitly trading delivery speed for energy efficiency. The matrix scorecard updates to add a third and highly demanding row: smart grid integration. The input required pulls you entirely out of standard software. You have to master distributed energy systems, hardware-adjacent networking, and IoT protocols. IoT, or the Internet of Things, refers to a network of physical devices embedded with sensors that exchange data over the internet. The outcome matches the difficulty. Heavy infrastructure sectors have deep funding for developers who can bridge the gap between code and physical energy grids, offering lucrative positioning as a specialized architect. The trade-off is the danger of extreme over-specialization. By focusing entirely on energy infrastructure, it pulls developers away from generalist software engineering, creating a niche lock-in. Smart grid integration offers the highest financial ceiling of all the green tech skills. It also leaves you with the narrowest career exit strategy if you ever want to leave the infrastructure sector. This decision tree maps who should take on these skills. It starts at primary career priority, splitting into rapid iteration or system optimization. If you are a front-end engineer, your path is rapid iteration. Your value is feature speed, so your result terminates at a pass. Spending hundreds of unpaid hours learning Power Grid APIs will not yield a financial outcome that matches your input. Companies will not pay you a premium to slow down their front-end user experience. If you are a back-end engineer, a data center architect, or a developer who gravitates toward deep, systemic problem-solving, your path goes down system optimization. Your result terminates at a match. Heavy industry and cloud providers are facing hard physical power limits. Developers who can solve those limits at the architectural level secure massive job security and insulation from broader tech layoffs. The transition to green tech is highly profitable, but you only realize that profit if you are willing to permanently trade your development velocity for deep architectural rigor.